I get, because of my conjugate complex numbers, I get negative I. I get those two when if I know one of them is complex, I get the other one. That means I have two of the four things. So I should be able to reduce this from a fourth order to a second order. If I have something that these two combine into, I should be able to divide this down to a second order. And what's great about a second order? Quadratic equation. Right? We worked long and hard on the quadratic equation, so this should be reducible. So we probably don't have to go through the rational root test. We don't have to do a ton of calculation with this, because we have one imaginary root. We get another one for free. Now, you could go through, you could find all the possible rational roots. You could work them through the remainder theorem. But there is a chance that this could all be imaginary too. So we want to work our way through and see what we can do with it. So let's see. If x equals I is one of my roots, then x minus I is one factor. And if the conjugate is a factor, it's going to look like that. Knowing one of them is I gives me that one thing divisible out of it was based off of these two components. And so I want to use that to be able to change my higher order. So let's FOIL this. So we get x squared minus I and plus I, the middle terms cancel. I get minus I squared, which is x squared plus 1. And so x squared plus 1 is divisible into this. So I can't use synthetic division, but I can use long division. So make sure I have each of my powers of x. And I look at the leading terms. If x squared goes into 2x to the fourth, that's going to be 2x squared. Multiply that back through. So we get 2x to the fourth plus 2x squared. I will change my signs, and I will subtract. So we get negative x cubed minus x squared minus x minus 1. I have a new leading coefficient. If negative x cubed goes into x squared, that's minus x. I multiply back through. Minus x times x squared is minus x cubed. Minus x times 1 is minus x. I change my signs. And I'll continue my division here. Negative x cubed and positive x cubed cancel, right? If we've done our job right, this term goes away. The minus x squared comes down. These cancel. Minus 1. Negative x squared divided by x squared is going to be negative 1. I multiply back through. Negative x squared minus 1. I change my signs and continue. And I get a remainder of 0, which is what I expected. So I have taken my fourth order polynomial. Knowing I had one imaginary root, I could reduce it down to a second order polynomial, which is here. So I'm going to rewrite what I know my factors are in the different forms I have them. So I know I have x minus I x plus I. And I have this 2x squared minus x minus 1. 2x squared minus x minus 1. Right. So I've taken a fourth order problem and I've turned it into a second order problem. And a second order problem is nice because we did all the heavy lifting to be able to use this. And so for this part here, A is equal to 2, B is equal to -1, and C is equal to -1. So I get x is 1 plus or minus 1 minus 4ac. So 4 times 2 times -1 is -8 plus 8. Over 2 times a is 4. So I get 1 plus or minus, this is 9, so the square root of 9 is 3, over 4. So 1 plus 3 is 4, so that answer is 1. 1 minus 3 is -2, and so that answer is -1/2. Alright, so that means I have factors of x minus I, x plus I, x minus 1, because solutions come over with a change of sign, and x plus 1/2. So my fully factored form of my polynomial looks like this. Or I could say my solutions are x equals plus or minus I, 1, and -1/2. We're saying the same thing when we do that. We're saying the same thing when we do that. All right. I'm going to do another one that has all imaginary roots, showing you this conjugate theorem and how it looks, and how we can build polynomials out of it. This one's a little messy. Let me get this up on the screen here, and then we'll do a full breaking down of polynomial at the end here. So again, we're recapping everything we have been doing. So let me flip this over to here. Yeah, all right. And so we're looking at number 13 here. Find a fourth degree equation with real coefficients with the roots 2i and 2 minus I. Now 2 minus I is going to be tricky, and you'll see why here. So 2i and 2 minus I. Whoops. 2i and 2 minus I. I need to start a new piece of paper here, I think. Is it filled up? So give me a second. So we have, let's see, this one that needs a bright cheery color. We'll go with yellow. So we have x is equal to 2i and x is equal to 2 minus I. Now, because of this, we get the complex conjugates, and so we want a fourth order polynomial. We're going to need 4 roots. Well, I get for free minus 2i. But this one's complex conjugate is 2 plus I. I have 4 roots now. There are no real solutions to the polynomial we're going to build. Again, we're using the fundamental theorem of algebra. We're looking for a fourth degree polynomial. So we need 4 roots, or a total of 4 with all the multiplicities involved. We have 2 distinct imaginary answers. So when we get their conjugates, we now have a total of 4 roots. And so those 4 roots will give us a fourth degree polynomial. And that fourth degree polynomial is what we want to hunt down. So I'm going to turn all of these into factors. So this is x minus 2i times x plus 2i. That gives me these factors. But these ones here, I'm going to do x minus, I'm going to keep this in parentheses for right now. And x minus 2 plus I. Nasty little bit of work there at the end, right? It's got teeth. It looks like anytime the number of symbols that we have go up, it can look a little bad back there. But what I want to note is this is a number and this is a number. And so we'll treat that as a thing. Alright, so I'm going to deal with this in 2 parts. So I want to make that part blue and this part orange, so we can do the parts together. So I'm going to FOIL this, so that's going to be x squared minus 2ix plus 2ix, the middle terms always cancel out, minus 4i squared. Well, I squared is negative 1, so this is x squared plus 2. Whew. All right, that was okay-ish. All right, so I am going to convert this thing here into x minus c, my complex number, and x minus the complex conjugate. I'm just going to get the pattern I want to work through here. So I'm going to get x squared is going to come out front. Okay. X squared. Whoops, put parentheses around these, sorry. I'm going to get minus cx and minus the complex conjugate. So I'm going to get minus cx minus the complex conjugate. And then in the end, I'm going to get this times its complex conjugate. Now the reason I'm writing those in notation is those parts have a lot going on in them. Oops, I forgot a letter X next to this one here. My apologies. But this thing at the end here, we know what's going to happen. Okay. A number times its complex conjugate, 2 minus I times 2 plus I, is going to be 4. Minus 2 plus 2, the middle terms cancel. And I get minus I squared, or plus 1. That becomes a 5. So instead of doing the 2 minus I times 2 plus I out at the end there, I just put it as the number times its complex conjugate. Remember back in chapter 3 when we were doing numbers and their complex conjugates, the whole reason we had a complex conjugate is when you multiplied it by its complex number, it would turn into its complex conjugate itself, it would turn into a real number. So I'm leaving all the ugliness here in the middle, but I'm simplifying my ends using what I know about complex conjugates. So what I have to do here now is I'm now going to have to replace this with C and this was C complex conjugate. Okay. So I'm going to have to replace these in to a subtraction. So minus 2 minus I times x, and minus 2 plus I times x, minus 5. That's my nastiest. So what I did is I used a smaller notation. I used a little bit of substitution to save me from having this polynomial really explode, and the middle term could be the nastiness. But one of the things that you will see doing multiplications and working with polynomials and anything that's quadratic or coming from binomials like this is the middle term is always where all the mess is. So if you can do things that get your ends kind of separated out and get your middle term dealt with separately or in its own right, you're going to be good. So x squared minus 2 x. I'm going to distribute the x through here and the negative, so this is going to become positive I, so this is going to be positive ix. Right, I put the negative through, that's negative 2, that's positive I. And I'm going to do the x at the same time. So x times that and x times that. So I'm going to distribute the negative through, that's negative 2. I'll also distribute the x. We could think about it as being like a negative x out front. And then in negative ix minus 5. Well, lo and behold, those two things get rid of each other, and I have that as my other factor. Now, some things to look at this, because this looks weird, right? You know, you haven't been doing loads of things with complex numbers or multiplying them, right? We did a unit on them, we did some homework on them, and I think I put a couple in the test as they came out of the quadratic equation. But this complex conjugate pairs now pop up in polynomials that we want to use some tricks out of them. And what is happening in polynomials is that if all of my coefficients are real and I get real solutions, I get the conjugate pair. That means when I multiply them together, I know I should have no imaginary numbers in my answer. So I'm taking this little theorem that we have, this fundamental theorem of algebra, and what does it mean to have a conjugate pair, and I'm showing you how it works its way back through the equations. And so having the conjugate pair here completely kills the middle term, right? But this was a completely imaginary number. Right, let's scroll back up here and find my scroll bar. There we go. Right? Completely imaginary number. It had no real part. This was a true complex number. It had a real part and it had an imaginary part. And so that real part kind of filters its way through this middle term and the complex conjugate. Now, I know, because of what we're doing, that this has to have real solutions. But I don't want to deal with this messy middle until I've fixed my end. And so I used the rule that the complex conjugate is always going to give a positive number. And we did that up above, and we get our minus 5, right? And then we come back here. So let's finish our multiplications. I'm going to multiply, and I'll do that in happy pink. No. What's a good color that comes out? I'll go back to yellow since we started in yellow, right? I just broke these two bits out. And I should have kept that in blue. My apologies. So x squared times x squared is x to the 4th. X squared minus 4x cubed. And minus 5x squared. So I'm taking the x squared to each term. And I'm going to take the positive 2 to each term. And I'm going to collect like terms. So x to the 4th minus 4x cubed minus 3x squared minus 8x minus 10. Looking for a sign error. X to the 4th minus 4x cubed minus 5x squared plus 2x squared minus 8x minus 10 fourth negative 4x cubed minus 3x squared. Where's the 5x? Yep. Minus alright. And checking my signs in here. Always check your signs. Sign errors are notorious here. So let's see, x minus the x squared there, minus cx minus 2 plus I, yep, minus 2 minus I, good, minus 4, and then in my end is a, nope, that should be positive. I knew there was a sign error here. There we go. Now here, right, I have warned you, sign errors are a thing, and I'm going to check for them, but here's how I checked, okay? All of my solutions, and this is the hard part about teaching, is making an error so you can show the tools you use to check without forcing the error horribly, right? Because sometimes when you force an error, it's not actually the actual error you do. Right? You have to kind of save your mistakes and go through here. And I know I'll make sign errors enough and they are so common that how you check them work. But what's important about this is I actually used a rule to check this. All of my solutions were imaginary, which meant that for Descartes' rule of signs, I shouldn't have gotten an odd number of sign variations. So here, if we apply Descartes' rule of signs, I start positive, I change to negative, I change back to positive. That means I have 2 or 0 real positive results. And I know because I built this off of imaginary that it had to be 0. I know a lot of the things we've been doing with Descartes' rule of signs, we've been getting odd answers for the number of sign changes, which guarantees that we're going to have a real or negative, a real number in our solutions. But when you have no real solutions, your number of sign variations should be even for Descartes' rule of signs. And so when I got down here and I had a negative 10 on the end, my sign changes were 1, and I knew it was wrong. And I knew I missed a negative sign, and the whole time I've been looking at this negative sign here going, this isn't right, this isn't right, there's something wrong about this. But because I wanted to focus on how we dealt with the middle terms, I didn't come back to it. So notice a negative times a negative should be a positive. All right? That worked out nicely. I got to show how one of our other rules can help us check things. And actually check a really complicated thing. That's a win. I'll take that win today. All right. Got 2 more I want to look at here as we review through everything we're doing. All right, I'm going to start with number 9 here, so we'll show that up here. Oh, no, I already did number 9. It's number 6. Find the zeros of the polynomial 8x cubed minus 14x squared minus 5x plus 2. All right, so this is a 3rd degree polynomial. We're going to talk about that. So let me write this on the blackboard bit here, and we're going to talk about what this is going to tell for us here. Get back here. So 8x cubed minus 14x squared. 8x cubed minus 14x squared minus 5x plus 2. This is the thing we want to factorize, we want to break down, we want to make it an easier thing for us to solve. So, I'm going to start with the fundamental theorem of algebra. And I want to say, hey, this thing has 3 possible roots. Now, because it's an odd number of roots, I have to have a real solution because complex numbers come in pairs. So just looking at it on a rough level, I'm either going to have 2 complex and 1 real, or 0 complex and 3 real. Those are my possible solutions, just looking at it without applying Descartes' rule of signs. Well, that's the next thing I'm going to do. I'm going to apply Descartes' rule of signs and see if I can eliminate negative or positive numbers, and see if I can kind of hone this in on particular values. So, Descartes' rule of signs says I count the sign variations in this for my positive results. So I start positive and I switch negative. That's 1. And I switch back positive. That's 2. So there's 2 variations. So I have 2 or 0 positive reals. Now, to find the negatives, I'm going to look at t of negative x. I'll look at t of negative x in happy blues. That changes the sign in front of the odd powers, keeps it the same in the even powers. And this has 1 sign variation, right? It's negative, switches to positive. So 1 variation. So I'm guaranteed 1 negative real result. So what I'm going to do here is I'm going to update that little table I made going back to the fundamental theorem of algebra. So we're kind of using all of our rules here to help us deal with this 8x cubed minus 14x squared minus 5x plus 2. Right? And what's nice is I've got 1 negative real result. I know for sure I have 1 negative real result. That's a guaranteed assuredness. And now because it was again a 3rd degree polynomial, I guess I could kind of say I was guaranteed a real result. And now I know I'm guaranteed a negative result, which means when I'm testing things, I know where to test. Right? I'm trying to narrow down what I can do here. So my complex, my positive reals, and my negative reals. So I know no matter what happens, I can have 2, 0, and 1. That adds up to 3. Or I can have 0, 2, and 1. That adds up to 3. I think those are the only combinations I can have. Because if I have 0, 0 positive reals, I have to have 2 complex and 1. Yep, that's it. Because it has to add up to 3. Those are my only possibilities. So I think I'm going to start hunting for the thing I'm guaranteed for. All right, notice my word choice around this. I'm thinking of a process. I'm thinking what the degree of the polynomial tells me. And then using Descartes' rule of signs to see if I'm guaranteed any real results. If I'm not guaranteed any real results, we get a bit more odd. But that means now that my leading coefficient and my constant determine all my possible rational roots. So I'm going to pull it down here. My leading coefficient, a sub n, was 8, and my constant was 2. Oh, right. Doesn't matter on sign right now. 8 and 2, yep. So all the factors of 8, my q's, are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And all of my factors of a sub 0 is plus or minus 1, plus or minus 2. So we're now using the rational root test. Okay. I'm trying to weave all these sections together. So my possible roots are all my possible p's over q's. So I'll start with q being 1. That means I have plus or minus 1, plus or minus 2, right? P over 1, P over 1. Now I will make 2, so I get plus or minus 1/2, and then plus or minus 1, but I already have that. Right? So I'm making my fractions. I start with this is my first set of fractions, which covers these two. I get 1 over 1 and 2 over 1. And I'll make this my next fraction. And I get 1 over 2, which is 1/2. And I get 2 over 2, which is 1, but I already have 1, so I'm not going to write it again. Now I'm going to make this my fraction, so I get plus or minus 1/4. And then I get 2 over 4, which is 1/2, and I already have that. And so now I'm going to use 8. I get plus or minus 1 over 8. And then 2 over 8, which is 1/4, which I already have. So 1, 2, 3, 4, 5 possible roots. Well, it's 10 possible roots, but I'm only looking at the negative ones. So what I want to do is I want to do t of p over q to find the remainders, and I want to keep the one that equals 0. And so I'm only going to pick the negative ones, and I'm going to put them in my calculator. So come back up here. I'm going to re-bring this equation back down. 8 cubed, 14, 5, and 2. 8, 14, 5, and 2. And I just need to check my signs out. I missed that scroll bar by a little bit. It says positive, negative, negative, positive. There's my t of x. Alright, and let me scroll up a bit. It's copying. There we go. So I'm going to put each of the negative values through. I'm actually going to start with the smallest. I'm going to go 1/8, 1/4, 1/2, and 1. I don't know why. That's the feeling I have. But I'm going to do this on my calculator. I'm going to do 8 parentheses negative 1/4 cubed minus 14 parentheses negative 1/4 squared minus 5 parentheses negative 1/4. And I'm doing the 4th. I didn't start with the 8th. I said I was going to start with the smaller. Well, I already have this mostly typed in. I'll do the 8th next. Alright, so I get (9/4) or 2.25 on my calculator. So it has a remainder at 1/4. So my option now is either to go to a 1/2 or an 1/8. I'm going to do a 1/2. Now what's nice is with my calculator I can scroll up my arrows here. I can use my scroll up arrows. And I could have. My memory's full. But I'll still do the 1/2. We'll get the 8th in if these other ones don't work, right? And this is where our remainder theorem helps us. I still want you to appreciate that in my younger school days, because I'm ancient and old, that we didn't have technology to help with these, and we had to do all these out by hand, and that picking and choosing numbers became a skill that you tried to find. I'm not sure if that skill had great advantage afterwards. And negative 1/2 is 0. So that is indeed one of our roots. Yay! I didn't even have the answer written down here. right? It's on my other paper, which I haven't shuffled to. But so we have negative 1/2. Well, that's good, because we're going to use this with synthetic division to get to reduce this from a third order to a second order. So, again, I'm going to keep recapping as we go through, because this is as complex as these things get, right? Is we have a polynomial, it's to a certain degree, and we need all of the roots. We look at the degree, and it's going to tell us what our possibilities is. If it's an even degree, there is a chance that we will have no real solutions. But if it's an odd degree, we have to have at least one real. So that was the first thing we looked at. We then used Descartes' rule of signs to see if we could guarantee if any one of them was a positive or a negative. And in this case, we were guaranteed one negative real root, one and only one. So that's why we tested the negatives using the remainder theorem. We use the rational root test. We take all the possible factors of our leading coefficient and our constant, and we turn them into a fraction, which is our p's and q's up here. And because Descartes' rule of signs says there is only one negative, we tested all the negatives. And we were only going to get one, and it happened to be negative 1/2. So negative 1/2 we have. Now we don't want to keep working with all of these cases. What we want to do is we want to simplify our problem. And so we're going to use synthetic division to turn this third degree polynomial into a second degree polynomial. So 8 times negative 1/2 is negative 4. I'll add these, I get negative 18. Negative 18 times negative 1/2 is positive 9. Get negative 4. And negative 4 times negative 1/2. Wait a minute, that's positive 4. Jeff can't add today. 9 minus 5 is 4. Negative 1/2 times 4 is negative 2, which is what I wanted to see. Because I know this is a root, I know the remainder is 0. I should be seeing 0 here. I use the remainder theorem to get this. Again, it's a way of checking my work, right? Noticing I make a sign change, a sign error, right? Coming across. All right, so I have reduced the order of my polynomial, so I know one of my solutions has a factor of x plus 1/2, or x is equal to negative 1/2, right? These are saying the same thing. I have one solution. My other factor is 8x squared minus 18x plus 4. I'm not going to play with Descartes' rule of sign. I'm not going to redo the rational root test to see if I have a smaller order of things to do. What I'm going to do is I'm going to use the quadratic formula. We spent all that time learning and investing in it, and it does get us somewhere. Plus, if I have imaginary roots in here, there are imaginary roots in here, I'm not going to see them with any other test. So, x equals negative b plus or minus b squared minus 4ac over 2a. A equals 8, b equals negative 18, c equals 4. So I'm getting 18 plus or minus 18 squared minus 4 times 8 times 4, 4ac, all over 16. All right, I'm going to get my calculator to simplify some terms out for me here. So I'm still going to have the 18 in the front, plus or minus, but I'm going to do everything in the square root now. Or as it's otherwise known, I'm going to do the discriminant, right? 18 squared minus 4 times 8 times 4 is 196. I think that's 14 squared, but we'll see here. So take the square root, get 14. So we have 18 plus or minus 14 over 16. And so I'll do the addition first. That's 32 over 16. That's one of them. This is the addition. Plus sign over here, right? 18 plus 14 is 32. Divided by 16, or 2. And now I'll do the subtraction. 18 minus 14 is 4. Or 1/4. And there are my two positive roots. And lo and behold, positive 1/4, positive 2. They were my possible solutions. And so now we can write everything we have. We have my negative root, x equals negative 1/2. My positive root, 1/4, and 2. Or I could write this as factors, x plus 1/2, x minus 1/4, and x minus 2. And so there are all of our rules coming together, and there are the manifestation of these rules. How we use the remainder theorem, how we use the fundamental theorem of algebra, how we use the rational root test, and how we can use our synthetic and long divisions to reduce problems. Now, the thing I am going to emphasize is I run towards second degree. As soon as I get second degree, the quadratic saves me. The quadratic saves me. And so I don't keep breaking things down. I have had some students that they'll take a second degree, they'll look for the rational roots in that and break down the rational roots and break down the rational roots and try to make it smaller and smaller and smaller and smaller and smaller. All right, so that's all I have review-wise. This gets us up through everything in 4 or 5. We will start rational functions next. Rational functions are a polynomial divided by another polynomial. And everything we did here still holds, because something really nasty happens whenever there's a 0 in the denominator. We have to have a hole in our domain. And that starts creating some weird behaviors. But that actually happens a lot in reality. Reality has things where things get so big they divide out, they create holes. They're called singularities, places where you're either dividing by 0 or you're getting infinitely dense, and the two things are kind of related. So being able to deal with rational functions and how they limit the values you can choose are a good mapping for a lot of things in reality that have limits in them. Population growth curves work on logistic models that have limited values that come through. A lot of that happens to how things divide, and in Chapter 5 we will look at logistic curves. This rational polynomials look and are a bit